We're going to wrap up this section by looking at one final example and try and bring in all of the same ideas that we've been looking at up until this point. So in this case, we've got college students may be interested in whether or not their majors have any effect on their starting salary after graduation. Suppose that 300 recent graduates were surveyed as to their majors in college and their starting survey after graduation. So we've got our different majors over here as our rows, and then some different salary ranges over here for our columns. So to start off, number one, we want to determine the degrees of freedom for this two-way table. Remember, our degrees of freedom is the number of rows minus 1 times the number of columns minus 1. So I need the number of rows and columns. So rows, remember, go horizontally. They're kind of stacked. So in this case, I've got 1, 2, 3, 4, 5 rows. So my degrees of freedom would be 5 minus 1, or 4, times the number of columns. I'm going to do that in red. We've got 1, 2, 3 columns right here. Again, we're not counting the total row and column. We only want to include where that data is. So in this case, we've got 3 minus 1 would be 2. 4 times 2, of course, giving me 8 degrees of freedom. So my degrees of freedom in this table is 8. If I was going to calculate the p-value by hand, this is something that we would certainly be interested in. This is something that would matter a great deal for us. So next up, we're going to calculate a few expected counts. So we want the expected counts for the nursing majors earning more than 79,000. So I want for this the row total times the column total, and then we'll divide that by the overall total. So in this case, my row total, we're looking at nursing majors earning more than 79,000. So that would be this entry right here. My row total is 40. So we've got 40 for my row total. 40 times my column total. Overall, the total number of people earning more than 79,000 is 130. So 40 times 130 divided by my overall table total. In this case, we've got 300 people in my survey. So let me grab my calculator real quick over here. We've got 40 times 130 divided by 300. I ended up with 17.33. I like to round to 2 decimal places when I'm calculating expected counts. If you wanted to say, oh, you can't have 0.3 of a person and round to the nearest whole number, I think that's certainly fine. That's a reasonable take. And then just one more to get a little bit more practice. In number 3, we're going to determine the expected count for the engineering majors earning less than 50,000. So if I look, my engineering majors earning less than 50,000, we're looking at this entry in my table right here. So my row total, we've got 100 total engineering majors, so 100 times the column total. The total number of graduates earning less than 50,000 would be 55 of those individuals. So 100 times 55, again divided by the table total. We said that was 300. It's the same as last time. So 100 times 55 divided by 300, and I ended up with 18.33. So our expected counts, that's something we should be pretty comfortable with, pretty familiar with. That's part of the process we would have to do if we were going to calculate the chi-square value by hand. I will not ask you to calculate the chi-square value by hand, but this is a part of it that we should be pretty familiar with. So now we're going to get into our actual hypothesis test. Number 4, it says perform a chi-square test to determine if college major and starting salary level are independent. We're going to use our significance level of 0.05. So for these types of problems, we already set our degrees of freedom, which I suppose we won't need if we're going to use our graphing calculator, but we will need our null hypothesis and our alternative hypothesis. So here are two variables that we're considering are college major and starting salary level. So if I'm going to talk about H0, we always begin by assuming that our two variables are independent. So we'll say college major, and starting salary level are independent, meaning there is no relationship between those two. The outcome of one of those things does not tell me anything about the outcome of the other. So there's my null hypothesis. My alternative hypothesis, HA, just says that those two things are dependent. So we're looking at college major, and starting salary level are dependent. You could also say they are associated. Again, there's lots of different ways that you could phrase this. This is just kind of the default that we're going to be using. So we always want to make sure we talk about what those two variables are. Make sure that we talk about those so that we know what they are. So we've got our null hypothesis. We've got our alternative hypothesis. Our next step would be to go and calculate the test statistic and the p-value. So we need our test stat. So our test stats, which is a chi-square value. So chi-square equals blank. And then we're also going to want to know what is the p-value for this particular test. If we can know those two things, then we'll be in really great shape for making our decision at the end of our problem. So just like last time in the last video, we're going to use our graphing calculator to find our test statistic and our p-value, which means we're going to have to enter our data into our calculator. Remember that we don't really care about this total row, or excuse me, that would be the column, this total column, and this total row right here. We don't want to include those with our entries when we create our matrix. We only want to include the data that we see, the actual numbers, not counting the totals. So in this case, we've got a 5 by 3. We've got 5 rows over here by 3 columns going across the top. So a 5 by 3, and if you need to pause the video for a moment so that you can reference that, or right above this, we should also have the table. That's what I'm looking at on my end. But I need to get my graphing calculator out. So to do that, hopping back over here, I'm going to go into my matrix menu. So if I press second and then that x to the -1 button, I'm going to arrow over to edit so that I can edit these matrix and I can put my data in. Now, in this case, our table is a different size than it was last time. So we're going to have to edit the dimensions. We said there were 5 rows by 3 columns. So if I change this one to 5, I should see some extra rows of zeros pop up at the bottom. We said 3 columns, so that's good to go. And then again, we're going to enter that data in our calculator exactly as we see it in the two-way table. We don't want to make any changes. So I'm looking at my end. I've got 5, and then I've got 20, and then I've got 5, and then 10, and 30, and 60. What else do we have? We've got 10, 15, 15, 10, 15, 15. We have 10, 20, 30, 10, 20, and 30. And then for our last row, we have 20, 30, 20. So 20, 30, 20 right here. So we've got all of our data entered in. That looks good to go. I like to quit back to the home screen, so I'm going to press second and then mode. And then at this point, I'm ready to go find my test statistic and my p-value. So to do that, I'm going to press stats We're going to arrow over to tests. And remember, we're looking for a chi-square test. So we're going to scroll down until we see that chi-square. Should be option C. And as long as you put all of your data into matrix A, we should not need to adjust anything here. We can leave observed as matrix A. Expected doesn't really matter. We're not going to use that. And then either calculate or draw. Let's just do calculate here. So in this case, they're saying that my chi-square test statistic is 33.55 if I round to 2 decimal places. And my p-value in this case, this looks a little bit funky, but let's talk about the test statistic first. We said 33.55. Let's get that down. So my chi-squared value is, we said, 33.55, which is very high. That's a very large test statistic. Our p-value then, what we're seeing in our calculator is 4.909, blah, 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 blah. And then at the end, you'll see that e minus 5. So that's scientific notation from the graphing calculator. I'm going to round this to 2 decimal places for right now. So this is 4.91, and then I'm going to bring that e negative 5. So 4.91. So 4.91 e negative 5. Now, I'm personally not a fan of this notation. I don't really care for it. What this really means is 4.91 times 10 to the negative 5th power, which, if you're familiar with scientific notation, you would say, of course, because our p-value, right, represents a probability. It shouldn't be greater than 1. It should be between 0 and 1, and it doesn't quite look like that's the case right now. But it's this 10 to the minus 5 that is going to kind of maybe potentially cause a little bit of confusion. What's really going on here is, if I take this decimal, when that I see that times 10 to the negative 5th, what that means is I'm going to take that decimal and I'm going to move it to the left that many times. So in this case, I'm going to move it to the left 1, 2, 3, 4, 5 right here. So what this actually represents, if I didn't want to write this with scientific notation, would be 0.0, so let's see, 1, 2, 3, 4 zeros. 1, 2, 3, 4, 4, 9, 1. 0.0000491. So an extremely low or small p-value that we ended up with here. It's not a very likely scenario at all. So our p-value is very close to 0. Remember that we said our alpha was going to be 0.05. So again, we're making our decision. We're comparing our p-value against alpha. In this case, the p-value is much less than alpha. So that means that we will reject the null hypothesis. We will reject H0, which means that there is enough evidence to support our alternative hypothesis. So if I want to scroll back up and look at that, that was that college major and starting salary level are dependent. So if we reject H0, that means that we've changed our minds. It means that there is enough evidence to support that college major and starting salary level are dependent. And there we go. That's the end of our problem. So hopefully the steps feel pretty familiar to the hypothesis tests we looked at in the last section. Obviously, using our graphing calculator does make calculating the test statistic and the p-value feel a little bit different. But overall, the steps are going to look pretty similar, where we need to set up our null and alternative hypothesis, calculate our test statistic and our p-value, and then make our decision, interpret the decision at the end of the problem.